Okay, welcome to Robotics 2. In today's class, I'm going to talk about the forces and moments. And then what I would do is I would talk about how to solve the project problem using MATLAB. So in today's class, what we are going to do is we will solve project 3 using MATLAB. But in next class, I will tell you using these MATLAB scripts how you can build the Simulink code. If you decide to start working directly on Simulink, most likely it won't work because there are a lot of subtle issues that you should be familiar, and unfortunately you may or may not be exposed to some of those concepts in EGR219 or other classes. So once again, project 3 is pushed, but I'm going to assign a homework that I would expect all of you to finish by Thursday so that you can take those scripts and finish project 3 by Saturday. So let's discuss what we were trying to do. Just from the beginning, this is the goal. In the last project, we numerically evaluated these differential equations. Yes, John, that is correct. It is not graded, but without finishing that homework, I don't think you'll be able to do the project. So if you look at this assignment and this entire chapter, we are trying to identify the values of forces F and values of torque L, M, and N. And this is what we started with. Forces, there are 3 types of forces: gravity, aerodynamic, and propulsion. So gravity forces are in inertial coordinate, aerodynamic forces are in stability frame, and propulsion forces are in body frame. Moments, there are 2 types. One is an aerodynamic moment, and the second moment is because of the propeller. Again, aerodynamic moment is in the stability frame, and the propulsion moment is in the body frame. So all these different forces and different movements, somehow we need to transfer to a consistent coordinate frame, specifically in this case the body frame, so that we get meaningful results. And in the last class, I kind of talked about different gravitational implementation. We talked about the aerodynamic forces. We talked about the concept of static pressure. We talked about the aerodynamic approximation. We looked at why the angle of attack is identified as negative. We looked at the concept of dynamic pressure, which is 1/2 rho VA square. We looked at the control surfaces for the conventional aircraft. We looked at the control surfaces for the V-tail aircraft. We looked at the control surfaces for a flying wing or Zagi aircraft. Now, we are going to talk about in today's lesson in detail about the dynamics in longitudinal and lateral plane. Now, when we talk about the longitudinal dynamics, we are looking at lift forces, drag forces, and moment. And one thing I want you to understand, that you have rho VA square, which is the dynamic pressure. When that is multiplied by the area, which is S, you get force. When that force is multiplied with a dimensionless quantity, please note, CL is a dimensionless quantity, coefficient of lift, which depends upon the angle of attack, pitch rate, and elevator deflection. Same thing, the drag force is dependent on angle of attack, elevator deflection, and pitch rate. Now, the only thing that I want you to be carefully observing here is, if you look at the moment equation, there is this additional dimension c, which is the chord length. Because it's a moment equation, so force needs to be multiplied by the moment. To answer Ghazi's question, there is a homework that is theoretically not due. That homework is just to get you prepped for the project. And the actual project that you will turn in will be due on Saturday. So there is no homework due on Thursday, but I'm just going to assign a homework so that you will be able to finish project 3 successfully. Does that answer your question, Ghazi? There is no submission on Thursday. But when we look at the Simulink code, we will use the homework or the code that you have written. And I will explain it to you as we go through the material. Now, I want to talk about these equations again. These are nothing but the linearizations of the lift equation. And we talked about CL, partial CL or partial alpha is nothing but the gradient or the slope of coefficient of lift with respect to angle of attack. Once again, partial CL divided by partial alpha is a gradient or slope, which is dy by dx, except dy is CL and dx is alpha. And please note, this is partial, which means when we evaluate this slope, the other parameters, namely Q and delta E, are assumed to be constant. That's why this is partial. And then I want you to understand that there is a scaling that appears over here. And this is something important. Why is this scaled? Please note, we want the quantities to be sort of dimensionless. In other words, when I multiply with Q, I want this resultant, once again, when I multiply with Q, I want all this resultant to be in newtons. Even though Q is in radians per second. Once again, I understand this. There is a scaling after CL, and the reason for that scaling is because Q is in radians per second. I want the entire product to be in newtons. Somehow I need to convert, or somehow I need to scale this Q into some sort of dimensionless unit. Now please note, VA, and this is important, VA is velocity in meters per second and C in meters. If you have C over VA, if you look at the scaling, that scaling somehow becomes second over 1. So this becomes second over 1. Now you will observe, and now if I use this scaling, I just have radians coming out of this approximation. There is just radians here. What comes out of this approximation is just radians, which is same as here, which is same as here. That's why for the scaling effects, you will have C divided by 2VA, which is the airspeed. And last, I briefly mentioned, and this is something that we'll talk about when we look at the stability derivatives, is this is nothing but similar to the Jacobian that we studied in robotics 1. Because please understand, just like Jacobian, I'm trying to find out the variation of coefficient of lift with respect to alpha, keeping all other parameters constant. Same thing with coefficient of drag, same with coefficient of moments. Now what I want to do is, I want to show you this complete linear aerodynamic model. And this is a linear aerodynamic model. This is a linear approximation. This is the linearization. So this linearization is valid only in small regions of alpha, valid in limited region. However, if you want to look at the behavior of lift force, drag force, and moment over a larger value of alpha, you will have to look at the complete nonlinear dynamical model. However, there is something else that happens when you increase the angle of attack. Now, please understand, if you have a small moderate angle of attack, the flow remains attached. So as you can see here, the flow is laminar and flow is attached to the wing. This is the ideal situation. You want flow to be attached to the wing. Only then you can apply the Bernoulli's principle. You are going to get pressure differential that will generate the lift. However, as the angle of attack increases, the flow starts separating from the wing. So as you can see, this is the turbulent region, which means flow is no longer attached to the wing, and which means all the bets are off. So when you have turbulent flow, you cannot predict the value of lift, drag, and aircraft would actually lose lift and it would fall down. That is something you will observe in if you fly RC planes. You will notice if you increase the angle of attack on the wing significantly, aircraft instead of flying up behaves like a rock and nosedive goes down. So it actually nosedives. So aircraft should be in the moderate angle of attack. It should not, the flow should not separate. But there are some aircrafts that are designed to operate in a high angle of attack, or fighter aircrafts. So for that, there are additional surfaces, control surfaces, fins, that make sure that the flow remains attached to the airframe and the wing. So what we do is, for the slightly larger angle of attack, we look at something called as the nonlinear model. Now, I want to tell you that nonlinear model is valid in certain regions. Linear model is valid in certain regions. For stall to happen, the flow first must become turbulent and then it will separate. If you have a laminar flow over a flat plate will not separate. Laminar flow is governed by low Reynolds number, rho LV divided by mu. So for laminar flow to become turbulent, you should have high velocity or you should have high angle of attack. Now, if you look at the nonlinear lift model, this is the nonlinear lift model. And this nonlinear lift model comes from the flat plate assumption. But what we do is, in order to approximate the behavior of the lifting force, we combine these two models. And this combined model is used for analysis. So the idea is, here is the idea. The coefficient of lift behaves linearly with respect to angle of attack in the small region near the equilibrium. So coefficient of lift is linear with respect to angle of attack. Lift force increases. At certain threshold alpha, even if you increase the angle of attack, the coefficient of lift suddenly drops down. That is loss of lift. That happens because of flow separation. So if you look at the nonlinear aerodynamic model is given something like this. Now, if you look at the expression for the nonlinear model, this is the nonlinear model, what you have is you have a blending factor that blends the linear model and the flat plate model. So we use this equation for analysis. So some of you may ask me, what is this equation telling us? This equation is nothing but mathematical representation of this curve. So if you look at this mathematical curve, this equation, what is shown over here with this blending factor, is nothing but mathematical expression describing the coefficient of lift with respect to angle of attack. So we use this equation to find out coefficient of lift at certain angle of attack, because as you know, if angle of attack reaches a certain threshold, the lift suddenly drops down. And you can actually use different values of m for this blending function. So if you look at m is just a constant in this blending function. Alpha and alpha naught, alpha is the current angle of attack, alpha naught is the threshold value of angle of attack when suddenly the lift force is dropped. And you have a blending function that ensures smooth transition from the linear model to the flat plate model. You can think about it something like when you are deciding or designing the trajectory for a robotic arm, you can actually blend different types of polynomials. And this is something like it is trying to blend different type of polynomials so that there is no sudden jump or jerks. Now, this is something interesting. The stability derivative. What is the point of using these equations? Okay, the equations are used because you cannot do wind tunnel testing for fraction of angle of attacks. Usually what you will do is you will have a standard airfoil like a NACA airfoil. And what you will do is you will perform the wind tunnel testing at 5 degrees angle of attack, 10 degrees angle of attack, 15 degrees angle of attack. Now you want to find out what happens in between. What would be the forces in between? And unfortunately, those forces are linear in a very small region. So if you look at the lift model that we have, from 0 to about 10 to 15 degrees, you can have the linear approximation. But to make sure that you have accurate estimation of the forces, that's why you use this linear model plus blending function. And please understand, for every airfoil, the parameters are different. For an example, the lift curve that I've shown you could be for a particular airfoil geometry. But as there are many types of airfoils, they are used for different types of planes. For an example, if you have a fighter plane, you want that to be super maneuverable. In other words, you want that plane to be borderline unstable, because what would happen is that gives you enormous maneuverability in when you fly that plane. So that is where these blending factors come in the picture. For linear analysis, you can stick to the linear model, that is sufficient. But if you really want to perform the analysis at high angle of attack or at high air speeds, then you would probably have to use a nonlinear aerodynamic model. If you are going to design or if you are going to study the complicated airframes, like maybe an Osprey or maybe X-plane or maybe a different plane geometry uh, or stealth plane, then you will have to use these equations. The next thing is, as we talked about earlier, as the coefficient of lift, as the lift force increases, the drag force also increases. So I want you to understand the coefficient of drag, CD, has two components. One is something called as the parasitic drag. That parasitic drag is dependent on actually the profile of the wing, friction and pressure. So if you look at the golf balls are dimpled to reduce parasitic drag. And if you, there is another concept which is called induced drag. That induced drag is actually dependent on coefficient of lift, the value of coefficient of lift. So CD alpha is dependent on parasitic drag, which is dependent on drag on the wing, friction, tail surface drag, fuselage, landing gear, so on. And the second part of the drag is because of the coefficient of lift. Now, this equation has something called as AR, which is nothing but aspect ratio, and E. E is called as Oswald efficiency factor. Now, please understand, we are trying to have a two-dimensional approximation for actually a three-dimensional phenomenon. So Oswald efficiency factor is kind of a correction factor that allows us to extend the result or analysis from three-dimensional analysis to a two-dimensional analysis. So E, or the Oswald efficiency factor, is nothing but the correction factor that is used in the drag equation. Now, what we will do is we will actually look at different lift and drag models. So very simply, a lift model and drag model can be expressed as a constant plus a gradient multiplied by the value of alpha. So CLO is nothing but the constant, and this is the slope or the gradient. This equation is valid for small angle of attack. Now you will see this term which is called as trim. Trim is nothing but equilibrium. Typically the dynamic equilibrium. So when you say the aircraft is trimmed, which means all the external forces on the aircraft are balanced. Now let's look at what are the forces acting in the longitudinal frame. And these equations are super important because we will implement these equations when we actually work on project 3. So please understand, we have a force in X direction, we have a force in Z direction. Force is because of the projection of drag and lift force. And the projection matrix is nothing but the angle of attack. So this is nothing but the rotation matrix that maps drag force and lift force to the forces in the body coordinate system. So it is very easy to see that you have a component of drag force going in this direction. You have a component of drag force which is going in this direction. You also have a component of lift force going in this direction, and you have a component of lift force is going in this direction. So I want you to note that this component and this component give you forces in the Z direction. This component and this component, they give you forces in the X direction. And it is nothing but just a simple projection matrix that can be done. The only thing I want you to understand is angle of attack is in the negative direction. And that's why you have sign flip on the off diagonal terms. And as you can see, some of you may clearly see that this is like rotation about Y, and that is true. The rotation is about Y axis, which is nothing but the J axis. So J body aligns with J stability. Now, what I'm doing in the next part is I'm just expanding the equation for drag and expanding the equation for lift. So this whole thing, so if you look at this whole thing, is nothing but the equation for drag, and this whole thing is nothing but the equation for lift. And this entire equation will be used when we try to solve the problem. But key parameters are here. So Q is the pitch rate, elevator deflection, Then you have the alphas, which are the angle of attack, and those will be used in simulation. Next thing is, how do we find out the pitching moment? Pitching moment is given by this equation, but the good news is the pitching moment is about the body axis. It's about the J axis. So pitching moment is about J, and J stability and J body, they are aligned. So that's why you do not need any rotational transformation, because J of body and J of stability frame, they are aligned. Now we are going to extend the same discussion for the lateral aerodynamics. So lateral aerodynamics means, so this is the plane. We looked at, now what we are going to do is we are going to look at the aerodynamics in the lateral direction. So this is lateral direction and this is longitudinal direction. So if you look at the lateral direction, you have Fy, L, which is the moment, and N, which is again the moment. So you have force in the Y direction and you have moments in the Z direction and X direction. So if you look at the lateral aerodynamics, the equations that you observe are exactly similar, except here is the difference. You have side slip angle, you have P, and then you have R, and you have aileron deflection, and you have rudder deflection. And if you look at what is P, P is nothing but the roll roll rate, and if R, it is nothing but yaw rate. P is about X body and yaw is about Z body. So what is happening here is the first quantity, which is the dynamic pressure, is remaining the same, 1/2 rho VA square. Dynamic pressure gets multiplied by S, which is the area that gives you the force in newtons. And everything else over here is nothing but a dimensionless quantity, which is obtained by a constant gradient of with respect to side slip, gradient with respect to roll rate, gradient with respect to yaw rate, and then you have aileron and rudder. However, there is something I want to point out, and this is absolutely you have to take note of. If you look at the scaling, scaling is with respect to B. If you look at the scaling in the case of moments, the scaling is with respect to C. So C is nothing but the chord length, and actually you will see that B dimension is the lateral dimension that you will use when you are performing the scaling, because this is the lateral aerodynamics. You cannot use a longitudinal dimension to normalize the lateral aerodynamic coefficient. If you pay close attention to the moments L and N, you would observe the moments are also expressed in the same fashion, except now rather than multiplying by C, these moments are multiplied by B, which is the lateral dimension. And again, entire expression is very simple. So when you try to program this, you will have to program this equation where the unknown will be beta, P, R, delta A, and delta R, and other coefficients will be given to you. If you look at appendix E, these coefficients are given to you. Now, few notes about the aerodynamic coefficients. There are some coefficients which are called as stability derivatives. And the reason for the stability derivatives, if you think about it, they actually determine the eigenvalues of the Jacobian. In other words, if you look at the stability derivatives like Cm alpha, Cl beta, Cn beta, those are longitudinal static stability, roll static stability, and yaw static stability. So these derivatives, for an example, Cm alpha has to be less than 0 for asymptotic stability. In other words, if the aircraft is in level flight at constant angle of attack, and if there is external disturbance that cause slight increase in the angle of attack, what will happen is aircraft on its own will have a downward pitching moment which will take it to the initial position. So which means external disturbance will not destabilize the aircraft if coefficient of moment with respect to alpha is less than 0. Same thing about roll static stability, which is associated with the dihedral. So this is nothing but the slope of the wings. We'll talk about it in just a second. And the last but not least is the yaw static derivative, which is dependent on the design of tail. If you look at a weathercock that shows the direction of airflow, that always gets aligned with the airflow because the path of the least resistance is in the direction of the airflow. So design of the tail dictates how the aircraft behaves with respect to the side slip angle. So beta is side slip. So the idea is if your CNB is greater than 0, and if you have sudden increase in the air velocity, that actually increases the value of beta or the side slip. If your yaw static stability derivative is greater than 0, aircraft on its own will go back to the initial position. And let me show this to you by means of some illustrations. So for an example, if you look at the longitudinal static stability derivative, you have lift and drag. These two forces act at something called as the center of pressure. Please note, center of pressure is behind the center of gravity. Center of pressure is behind the center of gravity. That makes aircraft stable in the longitudinal flight. That's why you would see many a times when the aircrafts are designed or the seat assignments are carried out, they make sure that the CG of the airplane is ahead of the center of pressure so that the aircraft is inherently stable in the longitudinal direction. So that causes aircraft to be stable. It is very typical in small planes. If you sit in a small plane, they will tell you that, hey, you need to put your backs in front, or if they expect the nose to be heavily loaded because that is where the engine is located. So that is the reason for that is you want the aircraft to be statically stable. If you look at the roll stability, dihedral is nothing but the slope of the angle of the wings. So if you see this wing is not flat. This wing is slanted upwards. That is called as dihedral. So it has some angle, and that angle is called dihedral. And the reason for that is if you follow the direction of small v, what happens is when the air velocity flows over wings, the leading and trailing wing, they develop a differential lift. For an example, leading wing would have a higher lift compared to the trailing wing, and that causes the natural roll stability. And if you have a dihedral, and if your CLB is less than 0, then what it will do is it will cause the aircraft to be stable in roll. So all of a sudden, if the aircraft gets rolled because of some disturbance, aircraft will return back to its original equilibrium orientation because of this stability properties. The yaw stability is with respect to the tail design. And once again, please understand this has to do with the side slip. So if you look at the side slip angle beta, that angle beta is positive with respect to the down direction. So in other words, if the value of beta increases, then you would have a differential lift on the tail, and that will cause aircraft to self-correct. In other words, because of some disturbance, if the aircraft gets yawed or if the aircraft get extra side slip, because of the, if C and B is greater than 0, then it will come back to its original equilibrium position. The next part is the dynamic stability derivatives. And just like static stability derivatives, CMQ, CLP, CNR. So coefficient of movement with respect to Q, coefficient of movement L with respect to P, coefficient of movement N with respect to R, they are corresponding to pitch damping derivative, roll damping derivative, and yaw damping derivative. And if you look at the differential equation of motion, you would realize that these will actually minimize the amplitude of oscillation. The control derivatives are nothing but the derivatives with respect to control input. So delta E, delta A, and delta R. So the Cm delta E is the coefficient of movement with respect to the elevator deflection. Cl is the coefficient of movement with respect to the aileron deflection, and Cn is the coefficient of movement with respect to rudder deflection. And these rudder deflection, aileron deflection, and uh, elevator deflection are the control surfaces deflections. So that's why they are called as the control derivatives. Now here is something I want you to understand very quickly. If you look at M is the moment about the pitch axis. So M delta E is the control surface that is controlling pitching. L is the moment about yaw axis. And I mean, L is the moment about the roll axis, and N is the moment about yaw axis. So these primary control derivatives are nothing but the derivatives with respect to the primary control surface. So for an example, pitching moment Cm is controlled with respect to delta E. That's why it is the primary control surface. Now, however, if you look at the secondary control surfaces, what you have is the moment is about different axis. For an example, the moment CL is L is the moment about the roll axis, but that is controlled by the rudder deflection. That's why this is called as the cross control. So if you look at Cn is controlled with aileron deflection. So that's why it is called as cross control. So primary control surfaces, the primary control derivatives are the gradient with respect to primary control surfaces. Cross control derivatives are the gradient with respect to cross control surfaces. The next part is prop thrust and torque. The purpose of prop. So there are two ways the aircraft could be propelled, and aircraft propulsion is a course in itself. But in this class, we are going to use a very simple propulsion uh, dynamics, which is the prop. So it's just like a fan, but the main purpose of prop is to give a thrust. Main purpose of fan is to provide the flow. So now here is the difference between the prop and fan. So you have a prop, which is propeller, and fan. The main purpose of fan is to increase delta V, increase the air velocity. So basically move the air. The main purpose of prop is increase the pressure difference. So delta P across the two sides of prop. So you would have P1 and you would have P2. So the main purpose of prop is to increase the value of delta P. And main purpose of fan is blow the air. And it may sound same, but functionality is different. And if you look at the way the blades are designed, the prop is designed differently compared to the fan. So a fan blade and a prop blade, you will see the angles are different, the orientations are different, the curvature is different, because these two have two different functionalities. Someone may ask, can a prop be used as fan and fan be used as prop? The answer to that question is no. If you put a prop on a fan, then you will notice that fan will topple down. If you put a fan blade for a prop operation, you will see that aircraft will not go anywhere. It will just blow air everywhere. So what I want you to understand here is there is a desired effect and undesired effect. If you have a prop that is attached to the plane, and I'm going to talk about the front prop. So if you have a prop in front, according to Newton's third law, every action is going to give you equal and opposite reaction. So what happens is when the prop is rotating, it's giving an equal and opposite reaction on the airframe. So what we need to do is this unnecessary, unneeded torque need to be compensated by a baseline aileron deflection, and that is called as trimming. Otherwise, what would happen is if you don't have trimming, then the aircraft will continuously roll, and you don't want that. So what they do is basically there are trimming tabs on the aircraft that are activated or aligned so that the counter torque is compensated. And this TP is nothing but the thrust, and thrust is nothing but delta P multiplied by the area of prop. Now, here are the equations, and these are the simple equations that I want you to understand and remember. Torque given by a prop, torque given by the prop is given as rho, which is the density of the air, n square, which is the speed in revolutions per second, which is RPS, and then d, which is the diameter of the prop, and Ct, which is the coefficient of torque for a particular prop. So once you select the prop, then Ct for that prop would be known. So if you look at a particular configuration of propeller, that propeller will describe all the design parameters and the value of Ct. So you can find out what would be the thrust that is generated by that prop at particular RPM. So please note, N is something that you control by means of throttle. So what happens is if you pull the throttle, then the speed of the prop increases, that increases the thrust, that increases torque. So the next thing is CQ, which is the coefficient of torque. It also depends upon the air density, the speed, but it depends upon the fifth order. And because of the dimensionality, thrust is in Newton, torque is in Newton meter. So you have diameter to the power 5. Now, one thing, angle of prop affects the value of Ct and Cq. And please note, in this class, we are talking about the prop that have fixed geometry. If you look at some exotic airplane design, where in certain cases, the orientation or the prop angles could be changed in the runtime, we are not going to look at that. As if you look at helicopter, you can change the angle of the prop using the squash plate in helicopters, but not in fixed wing planes or UAVs that we are studying. So the angle of prop, we will assume the all prop geometry to be constant. So which means if I give you a prop, we know what is the value of Ct, and that Ct does not change. What is the value of Cq, and that Cq value does not change. And when you study, if you study helicopter, You will also look at the concept of something called as J, which is called advance ratio. And that advance ratio is related to a non-dimensional quantity, which is airspeed divided by ND. In the case of helicopters, it is the tip speed, which is capital omega times D, the ratio of VA divided by tip speed. So, but in the case of uh, present study, we are going to assume the prop properties are going to remain constant and the thrust properties uh, are dependent on CT and speed, and torque is dependent on CQ and speed. We will assume rho to be constant, which is not really the case because the air density changes depending upon the altitude. If you look at, so the thrust formula can't be used for props that funnel the air thrust. I don't know what you mean by funnel the air thrust. So if you are going to use a prop and attach that to a motor, if you know the speed of the motor, if you know the diameter of the shaft, you can find the thrust. And that's what the prop is gonna give you. So if you look at the prop thrust versus torque, this is the relationship. You have CT versus advance ratio and CQ versus the advance ratio. And a lot of times, a lot of experiments are performed just like wind tunnel testing to find out these coefficients. And you will notice that CQ is actually dependent on this non-dimensional quantity, which is advance ratio, which is sort of a quadratic equation that is fitted in the experimental data. Now we are going to assume one simple observation that our UAVs, they are flown by a DC motor. So basically we have a prop. That prop is attached to a DC motor, and we don't assume an internal combustion engine, we assume a DC motor, so that our equations is significantly simplified. For example, the torque given by DC motor is given by KQ, which is the motor torque constant, 1 over R, which is the winding resistance, V in minus KV, capital omega. KV is the speed coefficient, so that depends upon omega, which is the angular velocity, and I naught, which is the initial current. So this is the equation that is used for finding out the torque that is given by the motor. And you might have seen exact same equation when you studied electric motors or when you looked at electric circuits. But please note, this product is nothing but back EMF. As you know, back EMF is required for the motor to run. V in is the supplied voltage and I naught is the base current. And when you multiply that with KQ, which is the motor torque constant, that will give you the torque that is generated by motor. So please understand, in simple words, torque is dependent on voltage applied. So if you increase the voltage or decrease the resistance, then your torque given by motor is going to increase. Now, what I'm going to do is, this is talking about the actual derivation of prop thrust and torque equations. And I'm going to skip few slides for now, but I will go back and pick up these slides later. I will discuss these slides again in next class. But what I want to do is, I want to talk about how do we simulate uh, the system that we have right now. So the last part is something I want you to keep in mind. We'll talk about this in next class, but the external wind also plays an important role, because the ground speed, if you look at the wind triangle, this is the ground speed, this is the air speed, and this is the wind speed. So what happens is, the amount of wind So for an example, if you get a tailwind or if you get a headwind, the amount of time you take to reach a destination is changed because the wind can either help you or hurt you. So what we need to do is we need to build the effect of wind into the design, but we'll talk about the wind models and how to incorporate those wind models in our simulation in next class. Now, what I want to do is I want to talk about the project a little bit. In this project, what we are trying to do is we are trying to first find out the different forces. We are going to find out Fg, which is the gravitational force. We are going to find out Fa, which we called as aerodynamic force, and then we will find out Fp or thrust given by the prop. So in other words, the equations that we saw, and let me talk about the equation that we saw. If you look at the aerodynamic equations, these equations, if you look at the longitudinal forces, this equation, and if you look at the prop, thrust, and torsions that we talked about here, that we need to program. And then understand there are interdependencies. So which means the prop and thrust depends upon the speed, but depending upon the thrust, the instantaneous values of state variables, they change, and depending upon the control input, uh, the pitch moment, roll moment, yaw moment changes. So you have a very complex system of equation that you should be able to run simultaneously. So what I'm going to do is I'm going to go to the MATLAB and I'm going to talk about how to simulate the, the project 3 in a MATLAB environment. And then I will talk about something called as object-oriented MATLAB that will be super helpful. And then we can talk about how to migrate all these codes and equations into Simulink environment. Before I begin, I want you to understand that this assignment may sound difficult or may look involved or tricky. It's actually not, as long as we follow a step-by-step approach. So what I'm going to do is I'm going to show my MATLAB screen. So you should be able to see my MATLAB screen. And if you look at my MATLAB screen, this MATLAB screen, you should have project 3 class discussions in folder. This project 3 class discussion folder is in the announcement, the latest announcement, and also it is part of the MATLAB scripts that I have uploaded. So before we begin, I just want to make sure that you have these files on the desktop. Right now, we are not going to MavSim. It's really difficult. So what I'm trying to say here is download project 3 class discussion.rar, expand it on the desktop, and then open that folder inside MATLAB. Does that answer your question, Ghazi? Okay. Everyone has access to these. Now, first and foremost, real quick, open simulation_run.m. The first file is simulation_run.m and hit run. And then you will notice that all of a sudden you are going to get lots of plots. And we'll talk about what these plots are. And you will also get a simulation. If you want to see the simulation for a longer period of time, change the time span from T0 to 5, run the code, and then you will see your UAV running for a longer period of time. Now, it doesn't show directly here, but what this tells me, if you look at the plot, if you look at figure 2, the UAV is dropping in altitude. So it is dropping in altitude. So that's what it is showing. But because of the scaling, it is not visible. So everyone, are you able to get this script running? Any questions? I will show you once again. If you change this value to say 100, 100, 100, and hit run, then you will see it running. If you change the orientation, you will see it's dropping in the altitude. So it kind of drops down. You should be able to get figure 2, figure 3, figure 4, and figure 5. If you are not able to get it, I will just copy my code and paste it over here that you can use in your simulation_run file. Okay. Now, what I want to talk about, it's first and foremost, let's go and look at UAV parameters.m. I want everyone to open UAV parameters.m. So this is called a class. MATLAB can do object-oriented programming. MATLAB has objects and MATLAB has classes. So what we are using this class to define the airframe properties. Once again, we are using this class to define the airframe properties. These are all the physical properties of the airframe aerosonde, or I don't know how you call this. So this is the airframe, and these properties are given in Appendix E. Now, one thing I want to show you that I change this value of gravity to 0. This has to be 9.81. MAV gravity is 9.81. Save this. Then MAV mass is 11 kilograms. Jx is the moment of inertia about x. Jy is the moment of inertia about y. Jz is the moment of inertia about z. So all these properties, they come from Appendix E. You used the similar properties for Zagi. So what I'm going to do here is, I'm going to show you the simulation for this aerosonde, and I want you to modify this file. So modify this file for Zagi. This is the homework I want all of you to do. So what you will do is, you will change, except the gravity, you will change all these parameters, because for Zagi airframe, the parameters are different. Then coefficient of lift 0, coefficient of drag 0, coefficient of M 0. These are all the aerodynamic parameters I have defined for aerosonde. That needs to be changed for Zagi. So all these parameters, they come from Appendix E. And last but not least, these are the prop parameters. You will also use Appendix E to change the prop parameters. Now, I want to repeat once again, this is a class. Now, this class has different members. So you have MAV gravity, MAV mass, MAV JX. How do I access particular property? Now check this out. The name of the class is UAV parameters and name of the property is MAV gravity. So if I want to access, I say UAV parameters. Once again, please look at what I'm doing. UAV parameters dot MAV underscore gravity. And if I enter MAV underscore gravity, yeah, can you see UAV parameters dot MAV underscore gravity gives me 9.81, which is the parameter here. If I go back and if I change MAV underscore mass, it gives me the mass. So what is the advantage of this approach? The advantage of this approach is you can change the simulation from Zagi to Air Sonde to some other aircraft very easily by just changing these files. So these values you can change and boom, your simulation would work. Also note that I am calculating gamma, gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6 for the properties defined in this file. So what it means is as soon as I change JX, JY, JZ and JXZ, all my gammas will be updated automatically. So once again, I would like you to change these parameters for Zagi using Appendix E. And the reason for that is this is actually called as a class, and these are the different members of the class. And the way you access the class member is just you access an element of a structure. But the good news with object and classes, you can also have the functions pertaining to that particular class. So you can actually call particular functions that belong to that class, and we will talk about it later. But before I begin or before I proceed further, I want you to understand that you can modify this for Zagi frame. So we replace them with the previous formula. Actually, I will answer your question in just a second. I'll answer this question in just a second. So any questions about modification in UAV parameters? So I want you to modify this for Zagi airplane. Next thing, what I want you to do is, I want you to open derivatives1.m file. Now, what I want you to note is something real quick. Is I want you to go through this derivatives1 file. This is exactly same as our derivatives file, except all the parameters are defined in terms of the members of the class. So please note, in the last simulation, we just use MAV mass. Here I'm using UAV parameters dot MAV mass, which is defined over here. So derivatives 1.m will directly grab values from UAV parameters and substitute over here. The position kinematics equation is the same. Position dynamics equation is the same. Rotational kinematics equation is in terms of Euler angles. That remains the same. But if you look at the rotational dynamics equation, that equation is rewritten in terms of UAV parameters dot MAV gamma 1. UAV parameters dot MAV gamma 2, UAV parameters dot MAV gamma 3, and so on. Now, next part, which, yes, that is correct. So UAV parameters is the file that will store the parameters for your airframe. So which means your simulation code derivatives 1.m doesn't have to be changed. You can just change the file, the parameter file, and it will run for the different airframe. Now, next step I want to talk about is we already know about this. The only thing is I want you to pay close attention to Fx, Fy, and Fz. And then I want you to pay close attention to L, then you have N, and you have M. So these are the moments. L, M, N are the moments, and Fx, Fy, Fz are the forces. If you look at this the code that we have as is, it is assuming the magnitude of forces and magnitude of moments is equal to 0. But if you look at the forces and moments, the value of forces and moments depend upon 3 parameters. First is the state. So essentially, the moments and forces depend upon the state. Then they depend upon the value of the control surfaces, which is the elevator deflection. Then you have the roll deflection, and then you have the yaw deflection, and you have the throttle. So delta I, if you look at these values of delta I, these are the nothing but the control surfaces. So if you look at, these are the control surfaces, and these control surfaces, they control the amount of Fx, Fy, Fz, L, M, and N. So now next thing is I want you to look at the wind. For this initial simulation, I'm going to assume the wind vector is equal to 0. So delta I are nothing but the first 3 are the deflections of control surfaces. For initial simulation, I'm gonna keep it as 0. Last one is the magnitude of thrust. All these values go from 0 to 1. So deltas can go from 0 to 1, 0 to 1, 0 to 1, and this can also go from 0 to 1. Wind is nothing but the wind vector, and that is all wind values are 0. So right now there is no wind. Now what I'm doing is I'm calling this function forces moment sp3. So forces moment sp3 is gonna give me value of fx, value of fy, value of fz, L moment, M moment, and N moment. So what I want you to do is, please observe the input to this function forces and moment sp is value of x, which is the state, which state comes from the current state of the aircraft, which means what is the forward velocity, what is the velocity in y direction, what is the velocity in z direction, what is the roll rate p, q, and r. So all these values are considered by this force moments function to find out the values of fx, fy, fz. And the last but not least is, what we need to do is we need to take the output of the force moments and map it to fx, fy, fz, l, m, and n. So right now what this code is going to do is it's going to take all these values. When it comes to this location, it will send all those x states, the control vector, and the wind velocity to force moments sp function, and the force moment sp3 function will give me forces in fx, fy, fz, and moments l, m, and n. Yeah, for the time being, it is from 0 to 1. So you can have 0, 0.1, 0.2, 0.3, something like that. But we'll talk about this in lot detail in next class. But now, everyone clear? Once you uncomment, what it means is you are getting the instantaneous values of forces 64, 65, 66, and instantaneous moment values of moments LMN, and they will be used in the next iteration fx, fy, fz, and l. But right now I want them to be 0 because there is one subtle thing that I want to talk about later. This code will be modified again little bit in next class. Any questions here? Okay, let's look at force moments SP3 function. Force moments SP3 function, what it's gonna do is it's gonna take the value of state, it's going to take the values of the control variable, it's going to take the value of wind vector. Wind vector is 6 vector. Delta values are the values of the control parameter. And if you look at what it's going to do is it's going to grab the value of x and map it to Pn, Pe, Pd, Uv, W, phi, theta, psi, PQR. And then I want you to note delta E, delta A, delta R, and delta T is all the delta. So first value of delta is the elevator deflection. Second value of delta is the aileron deflection. Third value of delta is rudder deflection. And fourth value of delta is the thrust. And the last part is if you take wind, you will actually map it to north, east, down, which are the inertial coordinates of the steady wind. And then you will have the gust, which is the body coordinate, or they are expressing the body coordinate of wind. Now what we need to do is we need to map the wind vector in the inertial coordinate. Please note, steady wind is always given in the inertial coordinate that needs to be mapped to the body coordinate. That's what is happening here. And then we use that to find out the relative velocities, UR, VR, WR. And we will talk about this in a lot detail in next class when we talk about wind. And then use all this to find out the value of VA, alpha, and beta. So what we will do is we will use these values. And please note, I just added the value of rho here. This rho is nothing but the air velocity, air density. So you have to change this value. So change this value for air density. Now Q bar, CA, SA, PQR, they come from the non-dimensionalization that we just talked about. So as you can see, there is a scaling factor here, scaling factor here, scaling factor here. That is non-dimensionalizing PQ and R. Then here, the gravitational force is mapped into the body frame. So I'm converting the gravitational force that is an inertial frame into the body frame. And then last but not least, I'm finding out the actual lift and drag forces in the body frame. So these are the lift and drag forces in body frame. And this is nothing but the equations that we talked about, they are programmed. And I would encourage you to go line by line. And this is something very important. I want you to go line by line and convince yourself that these equations are programmed correctly as per the textbook. These equations are given in the slide and the same equations are given in the textbook. So I would strongly encourage you to look at these equations line by line and make sure that I did not make any mistakes in sign. So I would encourage you to look at these equations for lift, drag forces, and moments. And if you look at the textbook, these equations are also given in the textbook. So please make sure that I have not made any mistake in sign. And you can look at these equations. These equations come from textbook page 49 and 50. 49 and 50. So these equations come from page 49, 50. For prop, these equations come from 53 and 54. And these equations make use of all the parameters that are in Appendix E. Now, I want you to observe. First, I'm finding out the lift force. I'm finding out the drag force. And then what I'm doing is I'm finding the component of lift and drag forces. And then I'm finding out the values of torques, T1, T2, and T3. So this script provides the aerodynamic forces and torques. Yeah, you would just use 1.22, that's fine. And last but not least is there is another function which is prop thrust torque. The input to prop thrust torque is the VA, which is nothing but the value of the voltage and the input, thrust input, voltage and thrust input. And the output of prop thrust torque is prop thrust, prop torque, prop speed, and motor current. And what you do is you add these forces to force 1 and torque 1. So the force in the x direction gets added with the thrust from the prop, and the moment in x direction is you subtract prop torque from the moment in the x direction. Now what I want to do is last function I want to talk about is look at prop thrust torque, and you would notice that I have programmed the equation that just we talked about, the value of KQ, value of V max, the value for A, parameters A, B, C, omega, and finally the output is thrust, torque, and current. And at this point, if you run simulation, in theory, this simulation is taking into account the magnitude of external forces. Now, at this point, if you really want to play with the simulation, you can change some parameters. Say you will add value of thrust is equal to 1, 0, run the simulation, and you will see some difference. That's it for today's class. So by next class, I want you to get this simulation running for Zagi airplane. And in next class, I will spend some more time talking about the interdependencies, because we need to modify these scripts, and then we'll talk about how to transfer these scripts in a Simulink environment. So I'm going to stop here.